Hello everyone. In this video, we are going to learn how to implement a traffic light control system in 8051 microcontroller. Now before we start writing the assembly program, we will learn what is this traffic light module. So basically our traffic light module is going to control the operation of traffic lights at a junction of 4 roads. So here you can see a junction of 4 roads. Right? Now we have to control the traffic in these 4 roads. Now we can also see that there are 6 LEDs in each corner, here, here and here. Okay. Now all these LEDs are controlled by port lines. Okay. These white ones which you see here are dual LEDs. They can show either red or green depending on the logic state. But the LEDs which are used here, they can show only one color. So depending on the logic state, they are going to either be turned on or turned off. Now a total of 24 port lines are being used here. There are 6 LEDs in each corner and there are 4 corners, so there is 24 LEDs. So for each LED there is one port line connected to it. So we want to develop a program which can control the vehicles coming from one direction in which the LEDs are present at the same corner. If the vehicles are coming from the east direction, the traffic lights which are here is going to tell the vehicle that either it can go forward or it can go right or it can go left or it has to stop here. So these LEDs are going to control the vehicle coming from its corner. Now what you can see here, this is called the Programming Peripheral Interface PPI. This is an 8255 PPI, and when we are writing our assembly language program, we need to specify for how much time we want each of the LEDs to glow, and also something like what ports we will be using to represent what LEDs and the mode of operation. So the data is going to determine whether the red LED is glowing or the green LED is glowing or the yellow LED is glowing. So programming this PPI is really important, and this is called the interface. We will connect this interface to 8051 microcontroller. So I had told that there are 24 port lines here. So for example, let me tell you some port lines. So we are going to be using 3 ports, A, B and C. Now these ports A, B and C are present in the 8255 chip. Now this chip is going to be connected to 8051 microcontroller. So these ports are used for interfacing to external devices. So the port A which we are having here is going to do some specific function. It is going to control the specific LEDs which are responsible for regulating the east and south traffic directions. And our port B is going to be responsible for regulating the LEDs for north and west directions. And our port C is going to be responsible for controlling any other additional traffic lights such as pedestrian crossing and some other additional traffic lights. Now in each port there are 8 port lines. So therefore making it 24 port lines. So port A is going to have port lines from PA0 up until PA7. So 0 to 7 there are 8 port lines, and port B is also going to have 8 port lines, so from PB0 to PB7. And port C is also going to have 8 port lines from PC0 to PC7. Now I told that port A is going to regulate east and south traffic. So east is here and south is here. So port A is going to control, for PA0 port line, it is going to control this LED, LED 20, which is the red LED. Now for PA1, it is going to control LED 19, which is the amber one. For PA2, it is going to control the green LED, LED 18. Now these 3 LEDs are for east coming traffic. Now this LED is for south. Now PA4 is going to be connected to the south red LED, which is here. So that's how the traffic can go either like this or in this direction. And PA3 is going to be given to the amber LED 26 for south. And PA2 is going to be given to this green LED. Okay. And PA1 to PA0 is going to be given to these. So we would have all the 8 port lines corresponding to all the LEDs here. Now similarly for port B, it is going to correspond to north and west, which is here and here. Now similarly, PB0 is going to correspond to this LED, and PB1 is going to correspond to this LED, and PB2 is going to correspond to this LED, and PB3 is going to correspond to this LED, PB4 is going to correspond to this LED, and so on and so forth. So what we want to do in this 8051 microcontroller is that we want to write a program which is going to control the turning on and the off of the given LEDs for a given amount of duration. Each LED has to glow for some duration, and this has to go in a loop. So now let's go into programming of the traffic light module. Now let's write the program required for controlling the traffic lights. Now here you can see that we have the 8255 PPI here, and we have 3 ports in it, A, B and C. Now we also have the 8051 which contains port 1, port 2 and port 3. Each of these ports have 8 port lines from PA7 to PA0, PB7 to PB0 and PC7 to PC0. Now port A is linked with port 1 and port B is linked with port 2 and port C is linked with port 3. Now the address location for port 1 of 8051 is E800H. The address location for port 2 is E801H. The address location for port 3 is E802H. And this location E803H is a control register address memory location for 8255. So all of these memories belong to port memory. And E803 is for control port, which is present in PPI. Now first I want to make use of DPTR. I'm going to point the DPTR to this location E803H. Okay, and for that I have to write MOV DPTR, hashtag E803H. Now I also have the accumulator register present in 8051, right? I am going to send a value into this accumulator register. I'm going to send a value of 80, move A, hashtag 80H. Now this 80H can correspond to a control signal which is necessary for turning on or turning off of the LEDs present in the PPI. So we have to send some data into the PPI, and corresponding to that data value, either the LED is going to get turned on or it is going to get turned off. So now A has 80H value and I have moved 80H value into A. Now I want to make this 80H go into the DPTR pointed location. So for that I have to write MOVX because I am accessing external memory, and I am going to write at DPTR, A. So from A I am going to get the value to DPTR. The value is 80H. 80H gets copied. So now in this location E803 I have a value of 80H here. Remember, this 80H is going to correspond to the control register. I told you, right? 80H is a control signal, and that control signal is going to be given to the control register. So this control register is responsible for turning on and turning off of LEDs based on the mode of operation. Now I want this traffic light to keep going in a loop. It is going to occur again and again in a loop. So I'm going to give a loop called again. And now I'm going to move this DPTR to some other memory location stored in 8051. So let's say I'm moving it to 9000H. This is a 16-bit address. So I have to tell MOV DPTR, hashtag 9000H. Now I'm going to define an inner loop within this outer loop, and I'm going to give the label next ST. So I'm going to give the label next ST. Now this next ST loop is going to make sure that some of the specific conditions are met before we are proceeding with the instructions which I'm going to give next. It is actually a mechanism for handling the states and errors if anything occurs efficiently. So in this loop what we are going to do is we are going to be comparing the port values and jumping with conditions or jumping conditionally so that our program can maintain a proper control over the traffic lights. Using the instructions which are given in nextst, we can also skip instructions based on what the comparison result we are going to get. So basically with this loop we want to get an efficient control flow mechanism. That's why we are using this nextst inner loop within the outer loop. So in this inner loop nextst I'm going to write MOVX A, at DPTR. So now I'm sending whatever value I have stored in 9000H into accumulator. Now for storing purposes, I don't want the data to get lost when we are moving these or copying these values into different locations. So now I'm going to make use of stack, which usually starts from 08H location in internal RAM. Usually internal RAM consists of 128 bytes and it starts from 00H and goes up till FFH. Now the stack pointer, which we use to denote to the top of the stack, is going to start from 07H, which means our stack's first location is 08H. And then it goes up until FFH. So initially stack pointer is going to point to the top of the stack, which is 07H. So whenever we reset the microcontroller, the stack pointer automatically points to 07H. That's why we tell the stack starting location is 08H. So if I want to store whatever I have in DPTR, I can only do it 8-bit at a time. So I should separate it into DPH and DPL. So DPL corresponds to 00 and DPH corresponds to 90. So first I'm going to send this DPL into the top of the stack. So DPL is going to come here. So I have to tell push DPL into the stack, and then I have to push DPH into the stack. So next DPH comes here and DPL is going to get above, so DPL comes here and the stack pointer is going to be here. Now I'm going to make this DPTR point to the address location of port A, which is E800. Very important. So now DPTR is going to point here, and for that I have to write MOV DPTR hashtag E800H, and this corresponds to port A. Now I had stored the value of DPTR present at 9000H in accumulator. So now I'm going to make the value present at accumulator to come into E800H, which is the location pointed by DPTR. For that I have to write MOVX at DPTR, A. So from A I am getting the value to E800H. Now if you remember, I have a stack where I have stored DPL and DPH. Now this stack is used mainly for storing and safeguarding the data from getting lost. So now I have to pop these values from the stack, because if I pop, then I'm going to retrieve the data DPL and DPH, and both these values are going to get combined and that will get stored in DPTR. You may ask, then why did we store it? We can just directly get it from A itself. But when we transfer such signals from A to DPTR, sometimes it may get lost. That's why we are storing it in stack, and when we need it, we store it, and when we don't need it, we pop it off so that it will get combined into the corresponding DPTR location. First I have to pop DPH, and then I have to write pop DPL. So now I have got the value to the correct address location of port A. And just like what I did with port A, I am also going to do with port B. Now when we pop this DPL and DPH, only the value is going to get stored in E800. What is going to happen to the DPTR pointed location? So DPTR is going to again go back to 9000H. So DPTR is going to show 9000H, and then we are going to increment DPTR. So when we increment DPTR, it is going to come to 9000H, which is the next location. So we store the value of DPTR in E800H, but at the same time we also made the DPTR point to the external memory location 9000H. Then we increment DPTR, and then we will go to 9001H location. So now my DPTR is currently pointing to 9001H location. Now the same thing which I performed for E800H, I have to perform for the next two E801H and E802H. So my DPTR is pointed to 9001H location. Now I have to send whatever I have in DPTR to the accumulator, and for that I have to write MOVX A, at DPTR, the same thing which we did for 9000H, and then I have to push the DPL and DPH to the stack. So I have to write push DPL and then push DPH, and then I have to move the DPTR to the desired location where we want the value E801. So for that I have to write MOV DPTR, hashtag E801H. So once DPTR is in this location, so I have to send whatever I have in accumulator to the DPTR pointed location, and for that I have to write MOV at DPTR comma A, MOVX, because we are accessing external memory. Now we have the value at E801H, but now we want the DPTR to jump back to 9001H, and at the same time I want the value to get stored in E801H. So for that I have to pop DPH and pop DPL, such that both DPH and DPL values are getting stored together in E801 and the DPTR goes back to 9001H. Now I am going to 9001H, and now I am going to increment DPTR. So now DPTR is going to point to 9002H. Now I have to again perform the same thing for the next address memory location, E802H. So the same code is again repeated. The only change is this, because now we want to store it to hashtag E802H. And one more thing, E801H corresponds to port B and E802H corresponds to port C. So I've done the same thing here. I've copied whatever I have written and I've changed the value here to E802. So now E802 is going to have the data value stored and the DPTR is going to jump back to 9002H. And then I am going to increment the DPTR again. So now DPTR is going to point to 9003H. Okay. Now I have to also configure the time duration for each of the turning on and turning off of LED. So I have to use delay instruction. So I'm going to write call delay. Now I have to define this delay, right? So for that I'm going to give the label delay here and I'm going to tell MOV R2 comma hashtag 06H. So I've used and register R2 present in 8051 to keep track of the delay I'm going to use for each of the turning on or turning off of LED. So I've given the duration 6, which is 6 seconds. So there will be a delay of 6 seconds in this turning on or turning off of LED. So this delay, when we call it, it is going to go to this location. I have given delay here itself because up until now is what we have done the turning on or turning off of LEDs. So after this, it is just going to be just configuration. It's not going to be the main program. Okay. So I've given delay here itself because above this, we have to perform delay because that is the turning on or turning off of LED. Now my DPTR is pointing to 9003H. So there is DPL and DPH here. I'm going to move this DPL into A. So I'm going to write move A comma DPL. Now I'm going to use the instruction CJNE, which means compare and jump if not equal. What I'm going to compare? I'm going to compare the accumulator value with 01H. And I'm going to jump to next TST, which is the efficient checking mechanism of the loop, inner loop. Next TST here is the inner loop. So I finished the inner loop here. So it is going to compare A with 01 and it is going to go back to the inner loop if they are not equal. If they are equal, it is going to continue below. Here we have used 01H because 01H is going to represent a specific state that the program is going to check. For example, 01H can represent a specific light signal, which is like a red light or a green light or a control command. Or it can be also used as a decision instruction. This 01H is going to determine whether we need to skip a certain block of code or we have to execute a certain block of code and jump to another part of the program. So it is just used for decision making also. And then I'm going to write the instruction sjump again. So this short jump again is going to create an infinite loop in which the LED is going to keep on switching on and off based on the patterns given to it. And that is what we wanted at the first. We defined something called again and then move x a comma at DPTR, right? So this infinite loop, we want to execute it continuously. So that's why we are going to end the outer loop here. Now outside the main outer loop, I want to create loops that repeat a block of instructions a specific number of times. So these loops can be used for managing the time or control sequences of traffic lights. So I'm going to give the name of the loop as first loop 3, and then I'm going to tell MOV R4, hashtag 0FFH. So I'm sending a value of 0FFH to the register R4. 0FFH corresponds to 255 in decimal. So I'm going to initialize R4 with 255. And then I'm going to define another nested loop, loop 2, in which I'm going to tell MOV R3, the same hashtag 0FFH. So I am initializing another register R3 with 0FFH. And in this I'm going to define another nested loop in which I'm going to perform decrementation of R3. So I'm going to decrement R3, then from 255 it is going to go to 254 in decimal. If we talk in hexadecimal, it is going to go to 0FE H. Now I'm going to compare this R3 with 00. And then I'm going to go to loop 1. Which means that I'm going to compare the value of R3 with the value 00H, and if it is not equal, I'm going to jump back to loop 1. So R3 and 00H are compared, and if they are not equal, we are going to jump back to loop 1. But if they become equal, then we move to the next instruction. If R3 becomes 0, it is going to continue forward, and then we are going to decrement R4. So R4 decreases from 255 to 254. If we are initialized 0FF to R4. And then we are going to compare R4 with 00, and if they are not equal, I will jump to loop 2. So R4 and 00H are compared. If R4 is equal 0, it is going to continue forward, or else we are going to jump back to loop 2 here. So once R4 becomes 0, we have to decrement R2. So decrement R2, and we are going to compare R2 with 00H, and if they are not equal, I am going to jump to loop 3. Since I had initialized R2 with 06 here, which is 6 seconds, now I have to decrement R2 slowly, and we are going to compare R2 with 0 seconds, and if they are not equal, I am going to jump to loop 3 here. So I am going to jump to loop 3, and this is really important. After R2 becomes 0, I am just going to end the program by saying return. So this is the program for traffic light controller. And when you are programming this in 8051, you have to clearly know the opcodes. The opcodes can be got by referring the opcode sheet given to you. In the practical demonstration, you will see the opcodes which I have used to get the result. Now I will send the values to these respective 9000H, 9001H locations So you can see 88, CD, 88, 81. These are all different values which I have given to the data memory locations. So with respect to this, the traffic light pattern is going to change.